What's up, team? Today we're doing some trig review. We're going to start talking about special right triangles, their connection to trigonometry, and then we're also going to talk about when to use the standard trig functions and when to use the inverse trig functions. So I'm going to start here by talking about special right triangles. I know you've seen these before. I just want to do a quick recap, and we're going to explore their connection to trig. So we have a 30, 60, 90. We have a 45, 45, 90. And these ratios are going to be true every single time you see triangles with these exact angle measures. So what does this mean? Well, if you have the short leg of a 30, 60, 90 triangle, if you know the length of the short leg, you know the hypotenuse is going to be exactly twice that length. And then the long leg, you take that the short leg, multiply it by root 3. Okay, fine and well. Well, let's do a quick example. What if we knew that the short leg had a length of 5? So we know these ratios exist. We get out a tape measure. We measure it. It's 5 inches or what, 5 units, whatever. So say that this is like 5. Well, that means the hypotenuse we know is going to be exactly twice as long every time we're in a 30, 60, 90 triangle. So the hypotenuse in this case is going to be length 10, and this other leg over here is going to be like 5 root 3. Of course, you can plug that in your calculator, get a decimal approximation. For the purpose of this, I'm going to leave it as is. For the 45, 45, 90 triangle, same thing, just a little bit different. Say we have this triangle, we measure our x. In this case, x happens to be 7. Just making up these numbers as I go here. We know if one of the legs has length 7, that the other one must also have length 7 because these ratios are given to us. And the hypotenuse of this one is going to be 7 times the square root of 2. So this is how we use right triangles. Special right triangles. Sometimes we're given different pieces and we have to do a little bit of dividing. For example, if we were given the fact that this one is 10, we would then divide it by 2, learn that this one is 5, and we can use that data over here as well. Okay, let's explore the connection between special right triangles and trigonometry that we've already seen. So again, none of the trig we're about to do is new. We're just kind of connecting some concepts with this part of today's video. So if you wanted to find the sine of 30, it's super tempting just to pick up the calculator, type in sine of 30, and it'll tell you what it is. And it'll be correct, absolutely, 100% of the time. But let's connect some dots between special rights and the trig stuff we've been doing. So sine of 30 means we're going to go to our triangle that has angle measure of 30. Sine, we know, is opposite over hypotenuse. So we're going to look at the opposite, which in this case, we're just going to keep it general. I'm going to leave it with the variables, and we're still going to be able to find our ratios. It's going to be pretty cool. So the opposite of 30, in this case, has length 5. We're going to get rid of all the blue stuff here. And the hypotenuse, the opposite is length x, and the hypotenuse is 2x. So the sine of 30, we can say, is x over 2x. Well, that's a little uncomfortable because we're used to seeing numbers. Notice there's some x's here that can cancel out. We have an x on top and x on the bottom. That this is going to simplify to 1 over 2. So for those of you keeping score at home that don't trust this necessarily, type in sine of 30 on your calculator right now. It's going to say 0.5 or it's going to say 1/2. For this reason, this is the exact reason why your calculator is saying that. It knows the ratios. Okay, cosine of 30, same thing but different. I'm going to start at 30, do adjacent over hypotenuse. So this one is going to be x root 3 over 2x. Again, the x's cancel, root 3 over 2. Gross. That's not a fun one to look at, but trust me when I say if you type in cosine of 30 in your calculator, you're going to get some decimal approximation. And then if you go type in root 3 over 2, you're going to get the same exact decimal approximation. They have the same exact value. The ratios are there. Okay, moving forward, tangent of 30. I'm going to try to pick it up here. Opposite over adjacent. So that one is going to be x over x root 3, which of course is 1 over root 3. Same thing applies. Decimal approximation of this is going to be the same as the decimal approximation here. Let's move to the 60-degree angle. Opposite over hypotenuse. X root 3 over 2x, which is root 3 over 2. No surprise that we have similar answers here. We know that when we have complementary angle measures here, the cosine of one is going to have the same value as the sine of the other. So we should see something similar down here. Cosine of 60, adjacent over hypotenuse, x over 2x, 1/2. Tangent of 60, opposite over adjacent is just x root 3 over x. So it's root 3 over 1. Oh, that's just root 3. That one's kind of nice. I like that one. Okay, let's look at the 45, 45, 90 triangle. There's less here because both of the acute angles are 45, so we're just doing half the work. So sine of 45 degrees, again, opposite over hypotenuse. We're going to do x over x root 2. X over x root 2, which is the same thing as 1 over root 2. So similarly, if you type in sine of 45 in your calculator, it's going to give you a decimal approximation that equals exactly the same as 1 over root 2. Cosine of 45, adjacent over hypotenuse. Turns out that's the same thing because the opposite and the adjacent legs have the same value. So I'm just going to skip to 1 over root 2. Tangent of 45, this one's a little bit interesting. Opposite over adjacent. You get to pick which 45-degree angle you're working from. Opposite over adjacent, that's going to be x over x, which simplifies to 1. The purpose of me showing you this is to show you the connections between trigonometry that we're familiar with, basic SOHCAHTOA, and the special right triangles that we studied previously. So a lot of times it's easy to compartmentalize. Okay, that was the special right triangle stuff. Forget about it. Now we're doing trig. Then we're going to forget about that and move forward. I challenge you to not think that way. All of this stuff works together, especially all this stuff with triangles. So the purpose of this was to show you the connection. The next thing I'm going to show you is when to use trig functions, the standard trig functions, and when to use inverse trig functions. Okay, a common question is, how do I know when to use the sine, cosine, tangent functions, and how do I know when to use the inverse sine, inverse cosine, inverse tangent functions? This next part should answer those questions. So, when to use each one? Well, use the standard sine, cosine, tangent when seeking side length. So if your objective is to find a side length, you are going to use sine, cosine, or tangent. If you're trying to find an angle measure, you're going to use the inverse sine, inverse cosine, or inverse tangent. Let's do an example, and well, actually I got 2 examples, one of each for you. So here's our first one, triangle ABC. It's a right triangle. It's oriented kind of funny, so we're going to keep in mind the hypotenuse is actually here on the bottom because it's opposite the right angle. We're given the side length of 8 over here, AB, and we're given this angle measure of 62, and we are given the task of finding the length of BC. So I'm going to go ahead and name this X, so I have something to work with here. I'm going to come at this from the perspective of angle A, because that's the angle measure that I have. I'm noticing that X is opposite of angle A, and the adjacent leg here is given to us at 8. So I'm going to use opposite and adjacent, thinking SOHCAHTOA. Tangent is opposite over adjacent. So I'm going to set this thing up. I'm going to say that the tangent of angle A, which happens to be 62 degrees, equals the ratio of the opposite leg over the adjacent leg. So tangent of 62 equals x over 8. One step, algebra 1 here, multiply both sides by 8. When we do that, we learn that 8 times the tangent of 62 equals x. That is our goal, is to find x. So I'm getting my calculator, and I'm going to type this business right in. 8 times tangent of 62 equals, and my calculator says that x equals 15.0045, so that rounds to 1505. Looking at what we have here, that seems reasonable. The short leg is 8, so this one must be longer. So x here is 15.05. There it is. I'm going to go ahead and pause, and we're going to wrap up with one more example. Okay, here we go with our second and final example. We have this triangle DEF. It's a right triangle. We have a leg of length 6.5, hypotenuse of leg 8, or length 8.5, and we're tasked with finding the measure of angle D. So that's this one up here. So we are finding an angle measure. That means we're going to use an inverse trig function. We just need to figure out which one to use. We have, well, as given, we only have one option because we have the opposite side to D, and we also have the hypotenuse. So opposite over hypotenuse is sine. We're going to use the inverse sine. If for some reason you really didn't want to use sine here, you could totally use Pythagorean theorem. Find the length of this leg, and then you have all the options. You could use cosine or you could use tangent if for whatever reason you chose to do so. Not interested in that. I don't really care which one we use. I'm going to use sine because that's what I can do with the information we have given. So we know that the sine of angle D equals the ratio of the opposite leg over the hypotenuse. Okay, fine. So notice how this is not the inverse sine. This is just regular sine. And I said a moment ago we have to use inverse trig functions for this one. Still true. Because this d right now, it's kind of trapped inside of a sine function. And we got to get it out. Because we're trying to solve for d. We're trying to find this angle measure. That's the whole objective of this particular example. So in order to get it out, we got to undo what's being done to it. Right now, we're taking the sine of d, so we're going to undo that and take the inverse sine of it. So if we take the inverse sine of the left side, that's going to cancel out the sine, and d is what remains. That means we have to do the same thing to the other side, just like any algebra problem ever. So we're going to take the inverse sine of the right-hand side as well, 6.5 over 8.5. And now we just have a game of pressing the right buttons on our calculator. So we know that the measure of angle G equals the inverse sine of this ratio right here, 6.5 over 8.5. So again, calculator, pressing the inverse sign, make sure it has that -1 on there. And I'm typing in 6.5 divided by 8.5. And I learned that the measure of angle G is, so the measure of angle G is 49.8988 degrees, just about 50 degrees. So this is 49.88 degrees. There it is. Use standard trig functions when you're trying to find side lengths. Use inverse trig functions when you're trying to find angle measures. Be extra careful with your algebra. Show some extra work if you're not sure. Check out the practice problems. Check out the notes. The solutions are posted. Let me know if you got questions. I believe in you.